weekly seminar series. The next week is finals. I'm John Karakis, one of the faculty members here, and I have the honor of introducing our speaker today, Dr. Martin Chamberlain. I've known Martin for a number of years. I can't exactly recall the last time we met, but certainly I've been up to Quebec City, and we scheduled him at this time of year where we might have snow or cold weather, knowing that he would not be afraid of that. As he was mentioning to me earlier, they have snow on the ground up in Quebec City, and it's been below freezing already. So this is warm compared to what he's used to. Well, Dr. Chamberlain received his bachelor's, master's, and PhD in electrical engineering from the Université Laval in Quebec City. And after he received his PhD, he went to work as a system engineer for Bowman. Bowman is a manufacturer of Fourier transform infrared spectrometers, FTIR systems. And after about 6 years there, for some reason, he got the idea to start his own company. So he was one of the co-founders of Telops and has been working there ever since. And so today we welcome him to hear a little bit more about infrared spectroscopy and the instrumentation and some of the phenomenologies that are associated with that. So let's welcome Dr. Chamberlain.
Well, thank you very much. Thank you for inviting me to come here.
Oh, I forgot something.
Yeah.
I have to interrupt you. I'm sorry. We also are using this meeting as a chapter meeting for the IEEE Geoscience and Remote Sensing Society. And as part of that, we need to report to the organization the number of IEEE members present. So I'll just ask your hand if you're a member of IEEE, and I'll do a quick count here. 1, 2, 3. Great, thank you.
Did you call me?
Sorry.
One more. Actually, one more. Okay, well, welcome everybody. Thank you for attending my presentation. So my name is Martin Chamberland. I am from Telops, a company in Quebec City. Just want to talk a little bit about the company. So we founded the company in 2000. 3 of us decided that we wanted to do some innovation in spectroscopy with thermal imaging. And we started the company. Now we are more than 60 employees. And I'll show you the great work that we're doing and the science that can be done with our products. So we mainly have 2 product lines at Telops, all oriented around thermal imaging, so imaging the thermal infrared band. So we do have all, let's say, high-tech cameras going from hyperspectral, multispectral, or very fast broadband camera. Just want to give you a quick example of measurements that are done with our broadband cameras, the fast camera. So here you have an example of one of our cameras installed to monitor the combustion inside the combustion chamber of an engine, so a diesel engine. So it's looking below the piston through some transparent material, looking at the combustion. And this is a very fast camera. And as you can see, you saw the diesel injection and the explosion, and all of that has been used in order to, let's say, improve performance of engines. So this is just example of what can be do with a thermal camera, and when you have access to very high-speed cameras like the one that we manufacture, it opens new research possibilities. But I'm here more to talk to you about the remote sensing with thermal hyperspectral infrared imager. So I just want to go quickly through the notions of the radiometry, the infrared spectroscopy, and the remote sensing, all that we have to deal with when you want to detect objects at a distance. And I'll show you applications, since the system has been in the field for more than 12 years now. It has been used for many, many different aspects. So let's start just a bit of theory, just that we put some name or the same vocabulary. So when we talk about infrared, I mean all of the electromagnetic spectrum which is above the visible light. So when we work in the infrared, it's from, let's say, 1 micron to 12 for our case. And we are interested in what the molecules do in that range. Since I came more from the spectroscopy side of things, we use more the wave number as the unit to measure like the wavelength of the light, or to let's say to characterize its frequency. So in physics, you must have seen many times lambda, or the wavelength, to measure the wavelength of the light. But in spectroscopy or in chemistry, we often use the wave numbers, and the units for the wave numbers are inverse centimeters. So you will see through all of my presentations, most of the time I talk about wave numbers. So this is where it comes. And if you just want to translate wavelength through wave numbers in your head, the equation is simple. So one is 10,000 divided by the other. So for example, at 10 micron wavelength is 1,000 wave numbers. So this is my anchor point I always remember. So just a quick introduction. So when we do, when we are in those range, so people doing spectroscopy, they talk about near IR, mid IR, and far IR for those wavelengths or wave numbers. And when we are in remote sensing, we commonly use those acronyms to define the bands that we are working in. So the veneer or the Visneer, it's from up to 1.4 micron. But at TELUPS, we mainly work in the mid-wave infrared and long-wave infrared, which is often called the thermal infrared. So from 3 to 5 micron and 8 to 12. And why there is a gap in between is because in remote sensing, the atmosphere is opaque between 5 and 8 microns due to the water vapor absorption in the atmosphere. I will also talk a lot about radiance and spectral radiance. So when I talk about radiance, it's the amount of power of a radiation which is emitted by a body that you can measure with your camera. And since I do hyperspectral, so I characterize spectral radiance. So it is the amount of power per unit of small band, or per unit of frequency. And I will also talk a lot about the temperature, but the units I use for temperature is Kelvin. So the Kelvin is it's absolute zero, is where there is no energy at all in the molecules. So it's the starting point. There is no negative temperature when you're in Kelvin. So the 0 Celsius, so where the water freezes, it's 273 Kelvin. And after that, like the boiling point is 373 Kelvin. So you will see on my slides a lot of results presented in Kelvin. So just remember that the room temperature is around 300 Kelvin. Okay, so let's talk about infrared self-emission. So what we have to know is all objects emit infrared radiation. So and the amount of radiation just depend on its own temperature, and it follows what we call the Planck curve, or the Planck law. So I have here an example of the Planck function for different temperatures. So at room temperature, it is this blue curve here, and you can see that the signal is mostly exclusively in the thermal infrared. Okay, in order to have signal, let's say at higher wave numbers or lower wavelengths, so closer to the decibel, it has to be emitted by something which is much warmer. So like the sun, it's close to 6,000 Kelvin. So, but when we talk about room temperature, it's really the signal that you get is really in a thermal or in a long wave infrared. And I want also to mention a notion called emissivity. So the emissivity is how much is emitted by a body. So like a black body has the maximum emissivity, which is 1. So when you're a black body, you emit the total Planck curve or Planck function. Okay, you're at 1. When you are a good mirror, a mirror doesn't emit at all. So a perfect mirror has emissivity of 0. So it just reflects. So anything in between is a mixture. And we have here an example of like asphalt is high emissivity, but it's not 1. It's not like a black body. Or like metals, like aluminum, reflects mainly. So it's a low emissivity. I have here other examples of emissivity, but I will go quickly through that. And just as I said earlier, a black body has this property that what you see from a black body is really what is perfectly emitted. So a black body does not reflect ambient radiation. Okay. Okay, and I think that's so. This here another basic theory. So just by conservation of energy, when you have some radiation, it's either reflected, transmitted, or absorbed. Okay, so and for energy conservation, the sum of all of this should become 1. So and when you have a solid object or even a gas, no matter. So what is absorbed is also equivalent to what will be re-emitted if the object is in thermal equilibrium. Because if it does not re-emit it, it will increase its own temperature. So that being said, when I have a solid, so there is nothing which is transmitted, so the equations, so the transmittance disappear. So what is emitted is 1 minus what is reflected. Okay? And for gas, so there is nothing reflected, so it's either transmitted or absorbed. So for a gas, so its emissivity will be 1 minus its transmittance. So that being said, I need to say that each molecule, because of their level of energies, depending on what they are, will have different level of energy which will absorb or re-emit light, and this is where spectroscopy comes from. So each signature, each molecule, has its own level of energy, giving rise to specific, let's say, wavelength or wave number that it will absorb or re-emit light. In the thermal infrared, in the long wave infrared, the main let's say phenomenon in the molecules are vibration. So we can even have stretch, asymmetric or symmetric, or the bending of those molecules, which give rise to those energy level and will correspond to their spectrum. So for example, if I have SO2 as a gas, and the SO2 molecule, here is its absorption spectrum. Okay, and again, here it is in wave number, but I have translated it in wavelength for you. So we see those little signatures there, and each of them are attributed to some vibrational mode, like here the asymmetric stretch, this one is symmetric stretch, here one is the bending. So the chemists understand very well this. So it's not my main background, but since I have lived with that, I start to understand that now. But the thing to remember is that the molecules each have their own fingerprint or a spectral signature. So these are just two examples here. For example, water vapor. So you see water vapor has a few absorption lines. And this is quartz, so solid like quartz. And generally, solids have smoother, let's say, absorption spectra than gases. Gas will have much narrower absorption lines. And this is my last theoretical slide. Just the atmosphere has water in it. It has a CO2. These are the two main gases in the atmosphere which absorb, so prevent you from doing remote sensing. But their absorption is localized, and so this is where we have these transparent windows where we do remote sensing. So one of them is the 8 to 12 micron, so this is what we call the long wave. So we have one instrument like the Hypercam long wave, which works in that band. And the other band is for the 3 to 5 micron clear window, and we call it the midwave, and we have one instrument called the Hypercam midwave, which operates in that band. We do have some other systems that goes beyond the midwave, very close to the shortwave. So here, 6,000 wave number is 1.5 micron. So we do have also systems that can measure into that range. But generally, the systems that measure in that range are for very high temperatures phenomena, like combustion and explosions and things like that. So this is the theory. Now let's talk about the instrument itself. So if you want to do remote sensing of these phenomena, you need an instrument to do it. So we designed in 2005 the Hypercam, which is a hyperspectral imager that operates in the thermal infrared. So many of you might be aware of dispersive systems where we have a grating or a prism or some optics that just spread light at different angles as a function of its wavelength. This is not the technology that we are using to build our spectrometer. We are using FTIR. So FTIR is a spectrometer that does interference. So the same light, the same scene that enters the instrument is split into with a beam splitter. And one arm is fixed, the other arm is moving. And what is important is the path difference between the two is such that it creates interference. So when the two beams recombine, we record the interference signal as a function of the path difference. And it is called interferogram. The interferogram, you do a simple Fourier transform on it, and magic, you get the spectrum. So this is how the instrument works. So the FTIR has been around for many, many, many years, and they used to be a single pixel, so single detector system. What we have innovated at TEDx, so we just produce images to the people that do spectroscopy. So people used to do spectroscopy with a single pixel. So what we brought to them is the same quality of spectroscopy, but with many pixels arranged in like an image. So we brought the imaging to the spectroscopists. So the Hypercam is exactly as I described earlier. So we look at a scene, split it into one arm, moves to create the interferogram, and we record not on a single detector, but on a focal plenary, so like on a camera, the signal. And for each pixel, we get what we call the interferogram. So when we do the Fourier transform, as I said earlier, we get the spectrum. So there are a lot of theories. So if you are familiar with Fourier transform theory, so all of the properties of the Fourier transform apply to this situation. So you have to sample, so you have to take images at a spacing which have to meet the Nyquist criteria. So depending on the highest frequency that you have in your signal, you have to sample it at least twice at higher frequency than that. The resolution of, so that, let's say that the bin spacing, so the number of bins that you will get in your spectrum just depends on the total length of your interferogram that you will measure. So the longer you measure your interferogram, the more bins, spectral bins you will have in your spectrum. So you can even have a system which is agile, like the Hypercam, where it's the user that decides today I want to make a measurement at that resolution, and you just change resolution just by changing the stroke length of the moving mirror. And the resolution is also given by the total length of your interferogram. So the formula is there. So what else? So once you do that, you do the Fourier transform, you get your what we call the raw spectrum. But we are doing radiometry at TELOPS with our instruments, so we need to calibrate them. So do the radiometric calibration. So by measuring, let's say, a reference black body, we know how to convert the raw spectrum into a calibrated spectrum using the Planck function for the black body. So in front of the African, we have black bodies like that. One is cold, one is warm, and it gives us two reference measurements, and it's pretty linear. Obviously, when you do remote sensing of ambient scenes, the two temperatures are generally very close to each other, and it is in a regime where nonlinearity can be ignored, and it works very well to do radiometric calibration just by measuring two reference black bodies. And we end up, let's say, with a complete hypercube, which is fully calibrated in radiance and spectrally, because Fourier transform has a laser inside the Fourier transform spectrometer in order to precisely measure the OPD, which is also my rule for my spectral axis. All of this being said, this is the Hypercam, which is a commercial instrument. So it was kind of unique because that technology used to be available only for the military people before TELOPS went on the market with a commercial camera that do hyperspectral imaging in the long wave infrared. So spectral resolution can be as high as or as low, depending on if you look at the units or the quality, as a quarter wave number. Quarter wave number in the 8 to 12 micron range corresponds to over 1600 bins, spectral bins. So it's a lot of bands to play with. So, we have a different telescope that we can install to change the field of view of the camera. We can operate it ground-based, airborne, and over the years we have developed all of the software to do real-time calibration, real-time gas detection, even from airplanes. We have several models that cover different bands, as I explained earlier. And recently we developed one specifically tuned on the long wave band of the methane. You know, methane is a gas which is of interest for the environment, for the greenhouse effect. So we developed a special system with more sensitivity to detect methane. We have several accessories that go with the Hypercam, including the airborne platform, polarizer. So some people have made research using polarization in addition to the spatial and the spectral information. So if you want to add more dimension, you can. And all of the software, I'll go quickly through that. And let's have a look at some of the data. What the data looks like when we look at a hypercube. Maybe I should say that if someone has a question, you can interrupt me anytime. And we will have a period of question at the end as well, but if a question comes up, don't hesitate to stop me. So, for those of you familiar with hyperspectral data, well, this is kind of the way we always see it. It's like an image, and we have the spectral information in a third axis. So we have two spatial dimensions, one spectral dimension, and we have here example. So if I have this chimney here, which is measured by the Hypercam, and I look at the warm side of the chimney, I have here in radiance unit, which is part of the Planck function, but I see the radiance coming from the outside, which is where I have my higher IS signal. And what I can see also in this, I can see those little lines here, which is water vapor absorption. So between the warm stack and the camera, there is water vapor, which is a bit colder in the atmosphere, and it absorbs the radiance emitted by the chimney. On the opposite, if I look here it's in the sky, the deep sky, so it's very cold, and I can see atmospheric ozone, which is warmer in the background, which emits its own signature. And I can see again my water vapor lines here, which are the same that I see here, but now they are in emission because they are much warmer than the background when I look at the deep sky. The other part of the scene are almost at equilibrium with the atmosphere, so this is why I don't see a lot of spectral features. We have several data cubes, and in fact I will give to John a USB key with a lot of samples of data cubes that you can use to do your research or try your own algorithms. But here there is one which I like a lot. It's an airplane that was just waiting. My airplane is here. So this is the viewer that we developed at TELUP. So I have loaded the airplane data cube, and what I see here, well, I see, for example, on the top of the airplane, so the airplane is like metallic. So in fact, when I look at those pixels, so if I select a pixel here, you have its spectrum here. So for each pixel, I have a complete spectrum. And what I see there, well, it's sky reflection. So I said earlier that metal does not emit a lot, it reflects. But the top of the airplane here reflects the sky. And what I see there is mainly the sky. So I see again my ozone emission and my water vapor here, which is like an emission because it's having the sky as the background. When I look at some warm places on the ground like this one, well, you see that now the temperature is much warmer. We talk about 303 Kelvin. And I see water vapor again, here water vapor in absorption in my spectrum. If I look here at the asphalt, so asphalt has the quartz response in it that I can see, and you will see it later in my presentation. But in that part of the spectrum, the quartz or the asphalt has high emissivity, so I see roughly its temperature. But in this region, it's like a reflector. So yeah, I can see again my sky with my water vapor. So at those wavelengths, if I look at an image at those wavelengths, you will see now that the asphalt appears cold, but it's not cold because its emissivity is really low and it reflects the sky. Okay, if I go back to where asphalt is with high emissivity, now it appears warmer. So again, and this is a notion that I will explain a bit later. When we want to measure temperature of something, we have to do the temperature emissivity separation, not just to look at the signal as a whole. When you have the spectrum, you can really extract its emissivity and get its real temperature. And here we have combustion. So, oops, sorry, it's saturated, but we do have combustion where the engines, where we have like water vapor, which is much warmer, which is emitted. Again, you can see the temperature, it's over 250 Kelvin. So it's only the apparent temperature of the gas there, again, depending on its emissivity. It's not its real temperature. So let's go back to the presentation. So the system also as you understand, the interferometer, it takes a complete image at each OPD. That means that we also have the temporal information of a scene. So here you can see the interferogram when it is built, but you can see also that we have very high-speed video of the engines burning fuel. So the system, in addition to measure spectral information in real time, simultaneously, you get very, very high-speed video. So for the long wave system, it's close to 300 hertz when we are full frame. And for the mid-wave system, it's even faster. We can go over kilohertz of image rate.
Are measuring this out of the entire image or the single pixel?
This frame rate?
The spectrum just.
No. So we record all of the images at those frame rate, but it can take like half a second to acquire, like, let's say to build a long wave spectrum, let's say I need 300 images. So it will take me 1 second to record the 300 images. So during that time, I can look at them individually and I get those high-speed video. But during that 1 second, after that, I use those 300 frames, I do a Fourier transform, and I just get one hypercube. So the hypercube rate is like just 1 hertz. So
Like you're measuring an interferogram for every pixel, right?
yeah, oh yeah, absolutely. So after 1 second, you get, if you are in 320 by 256, you get 80,000 spectra. So 1 spectrum for each pixel, and each spectrum has like 200 spectral bits.
Could you stop it at coherence spike so that it looks like it's flashed there?
Yeah, absolutely. In fact, I'll do better than that for you. I don't have it. Can I do it? So, and you saw very well. Well, but yes, you're right. So here it is. Because the camera is behind the interferometer, around what we call the ZPD region. So ZPD is the zero path difference. It's the exact position where your two arms in the interferometer are exactly the same length. There is a lot of interference pattern coming there. So most of the information is there. And so this is why when you try to do a non-uniformity correction of the signal, we still get some residuals. And you see it flashing in the video.
Isn't all the information there and the rest of it is kind of redundant?
No. The only thing which is redundant is the right side and the left side. Okay, because for a real signal, interferogram is even. So that means that you should get exactly the same signal on both sides. But no, it's resolution. So the point at ZPD is the equivalent of the total energy. So it's like the integral. So it's like your DC. Okay, and after that, it's all spectral information or more and more resolution.
You have another question?
Yeah, no problem. Oh, sorry. Yeah.
I noticed the flickering of the exhaust. Can you determine what that frequency is?
Well, yes, we can, but not now. But
Yeah, I understand that.
Yeah, because each image has a precise timestamp, so we know exactly the time between two images. And I'll show you later another application where we clearly use that information to measure velocity.
Okay,
Yeah.
thank you.
Yeah, we can do it. So this is another strength of that type of system, because we have simultaneously high-speed video and spectral information within the same instrument. Good. Okay, so the first application that I want to present you is gas detection. Okay. So here is the situation. We have our camera, and we receive some radiance. So the radiance that we get is this signal here, the total radiance, but it's a combination of a lot of things. So we have a background, and now that you know that depending on emissivity, well, the background does not just emit, but also reflects what is downloading onto it. So you have this complex background signal that propagates and go through, let's say, a gas cloud that you want to detect. So this is my background is transmitted through a gas which has some transmittance. All of these variables are spectrally dependent, so are a function of wavelength or wave number. And because the gas cloud is at thermal equilibrium, so what is not transmitted is emitted. So 1 minus its transmittance is what is emitted by its own temperature. And all of this signal propagates and has to go through the atmosphere, which a given transmittance. And because the atmosphere is at equilibrium, temperature equilibrium, well, what it does not transmit, it emits. And this nice little signal is what you have as the at sensor readings. And what you want to do is to detect gas to see, hey, do I have that gas there in my scene? So it's possible. And just a quick, so for example, if we look at the moon, so from the Earth, we go through the atmosphere, and you have here an example. So if I have the moon, let's say, as the background, which is a bit warm, I see that type of signal. And again, I go through the ozone. So you have here the reference spectra, so taken from a library. So you have here the ozone absorption, and in blue, the water vapor absorption. And this is exactly what you see when you look at the moon in that band with the hypercam. You see ozone, which absorb the light coming from the moon. And you see all of those water vapor lines. And if I look at a point in the same scene, but which is outside of the moon, so I see the deep sky. Deep sky is very cold, and now the same gas, because a few millirad away from the moon is exactly the same atmosphere that I was looking at. But you see, I have exactly the same gases, but now I see them in emission because they are warmer than the deep sky. So here I see my ozone, which is in emission, and I see all of my water vapor in emission. And the reason why, okay, and last thing I want to say, so in the area where water vapor absorbs the most, so the atmosphere is opaque, so I don't see up to the moon. So what I see, it's in this region here, you can see that both or in front of the deep sky or in front of the moon, I see exactly the same signal. In fact, I see just the gas, just the water vapor, and I can just measure the temperature of the gas at that place, which is 209 Kelvin. So, for example, this data cube is on the USB key that I will give to John. Another example here is, for example, methanol. So if we have an experiment here where we have methanol, so methanol is like a liquid, like a solvent, but the vapor from the methanol just evaporates, and we can detect it. So we have here an example of that. I have other examples. For example, here, if we just pour acetone, and acetone absorption is here, methanol absorption is here. So we pour them on the asphalt, they start to evaporate, and we can detect them. So just let me show you that. So, so again, I am in my viewer, and I did a trick. So what I did, I decided that my spectrum, even though it has a lot of spectral bins, I will select a few bands, 3 bands, and I will attribute them a color in the visible. So I can do a false color image built on this long wave infrared information. So, and I just on purpose put one band where methanol absorbs and one band where acetone absorbs. And you will see the 2 gases, when they evaporate, they will just show like colors. So this is like a simple, let's say, gas imaging, okay? And again, just because, and if I go over a pixel, which is more red like that, so here I have my methanol signature that you can see. And here where it's yellowish, it's more like my acetone absorption that I see. So you understand that in these scenes, I do have like a complex signal, radiance coming from the asphalt, reflecting the sky, the gas in between this background. But now that you understand that all of this radiance, how it is transmitted, well, we can recognize the signatures of those gases, and this is how we do gas detection with remote sensing.
How many parts per million do you think you could?
Well, it depends on which gas. So because each gas have different strength in absorptions. So, for example, for methane, I will show you that our system is capable of detecting down to the ambient level of 1.8 ppm. And again, this is a passive system. So the strength of the signal that we get at the sensor depends on the thermal contrast between the gas and the background. So if we're not lucky at all, the background is exactly at the same temperature as the gas cloud, and there is no contrast, we don't see it. If we're lucky, we have a very warm background, and at that time the signal is multiplied by a good factor, and we see it, and we have a better sensitivity. So this is my solvent. And this is another example, similar to the one I just showed you, but from a distance of 1.8 kilometers, we detected SF6 release. So they started with release of SF6, so this is accelerated, and a minute after that, they added ammonia. And so this is, you can see the gas cloud, how it dispersed following the release. So you can imagine that we can have algorithms that just compare spectra from the pixels to a library of reference spectra, and if they match, we just color code the pixel according to what we have detected. So we have developed a software that we call the Reveal DNI, and the software does that in real time. So in real time, you can look at a chimney out of an industry and measure exactly what is coming out of that chimney. And they don't know that you're doing that. You can do that from a few kilometers away. And so you don't need to go onto their property in order to do that. So we can do a pollution monitoring or try to find people that do some processing that they are not supposed to, and we identify them. So since we have the complete spectrum and we have good radiative transfer models, well, we can use those equations and knowledge of the physics in order to build a model and try to fit a measurement. 5 minutes. Yeah, I still have. Thanks. Yeah, so and when you do that, well, the numbers that you put in your equations such that the measurement and the model fit perfectly, and this is an example here where in blue is the measurement and in green is the model. When they fit perfectly, it's because you put the right gases with the right amount and the right temperature. And this is one way, using the same data sets, to quantify the quantity of gas that you have in your scene. So we did that. For example, we have a local incinerator in Quebec City, so we went there and we measured all of the gas that was coming out. So even we have temperature of gas concentration, and we were able to quantify what was released by the incinerator. Earlier I said that we have a methane instrument. So our methane instrument was originally developed for a university in Sweden, so the Linköping University, and these people have made a really good, let's say, measurement and publication in Nature, where you can see here how much methane is released during the melting down of a lake at the springtime. So ambient methane is 1.8 ppm. So here, where it's red, it's only slightly above 1.8, it's 2.05 ppm. So you can see that the system is very, very sensitive to detect methane as well. So regarding methane, I will just, I just want to show you. Do I have my methane? Yeah. So earlier I said that I just want to show you. So with the methane system, for example, you can see we participated to a trial where they wanted us to measure the leak rate. So this is, again, the video. So it's not the spectral information, so it's just the high-speed video. As you can see with the high-speed video, we can see the gas. And with we are using this to measure the velocity of the gas cloud, in addition to the grams or the mass that we determine with the spectral information. And when we combine both, we can measure how much gram is emitted per second. So using both spectral and temporal information. So let's go back there. So I will go very quickly through the last slides. So again, we do quantification. We used it for several surveys of methane, and even we participated at a trial with Total, which is an oil and gas company in France, where they have installed 3 hypercams and they do tomography. So they are able to do 3D reconstruction in real time of methane. So this is how they want to use, for example, the hypercam technology. If there is a crisis somewhere, they just want, let's say, to fly over and localize and quantify the amount of methane which is released. So, we participated to volcano measurements. So volcano, they emit a lot of SO2, but other stuff. So yes, the hypercam, again, those molecules are in the spectral range, and we did that. We can fly the hypercam, so all of what I've shown up to now were ground-based measurement. The same camera can be installed in an airplane, fly over some sites, do some mapping or some targeting, and do very nice maps that we produce with the hypercam. And remember, each pixel is a complete spectrum with 100 band. So you can do spectroscopy on that to do gas detection. So this is the famous incinerator in Quebec City. Again, we flew over and measured the gas release. And we did an experiment last summer where we developed our gas detection system to operate in real time in the aircraft. So we did some release of ethylene and methanol and acetone, and you can see here from airborne measurement the detection and identification of those gases. when we are in targeting mode, well, we see, again, when we're targeting while flying over many frames, we can see the gas cloud. We did that over the refinery close to Quebec City, so all of this data will be on the USBT. The Air Force Institute of Technology, they have also Hypercam that we deliver to them, and the characterized combustion of jet engines or flames and things like that. So they do a lot of spectroscopy around combustion. Last thing I wanted to present, since I still have just 1 minute left, is we can also measure solid with it. So instead of measuring transmittance through the gas cloud, we can just look at solids and try to estimate its emissivity. So similar equations apply. Have to take into account that the signal goes through the atmosphere again to remove all of those contributions. And so so you have like quartz that you want to observe, and it is reflecting the sky, is transmitted through the atmosphere, and the signal that you get looks like this one. And remember when I show you the airplane with the asphalt, this is exactly what we were seeing. So when you do temperature emissivity separation, you start from this and you try to remove this to get that. And once you get that, you have identified the solid that you have in your field of view. So similar equation and examples of measurements we did. We worked with the spectral science to develop the CIS algorithm based on some Borel equation. And well, so I can show you examples that we did it. And for example, this one in Switzerland, in Zurich, where they have a mine and they wanted to distinguish between dolomite and calcite. So those are two very similar things, and we can map where we have dolomite and calcite, and because they want to avoid putting calcite for the concrete when they do concrete. So mine phase, we did that a lot, and we did also airborne. So if you see you saw gas airborne, we can do geology or minerals airborne as well. So I have examples, and so let me go very quickly. So for example, when so this is the result of the CIS. So once you have remove all of the atmospheric contribution, what you ended up is really emissivity of the ground. And for example, it is a granite and so maybe it's quartz and serpentinite, which is something that goes into the asbestos. So and this is the thematic mapping of those different minerals around the mining area. And finally, once you do the temperature emissivity separation, instead of having the full broadband signal, which is the apparent temperature, but which is not the real temperature of the object, when you do temperature emissivity separation, the temperature that you get is really the real temperature of the object. And we have characterized the urban heat islands with that. So from our airborne survey. So here is the apparent temperature as it is broadband, but once you do the temperature emissivity separation, these are the real temperature of the objects on the ground, which is much warmer. So to conclude, as you can see, thermal infrared hyperspectral imaging is a powerful technique for remote sensing. The gases can be detected, identified, quantified remotely. So the Hypercam is an outstanding research tool, and I will leave that sample data sets so that you can play with. Thank you.
I think you taught folks here. That was excellent. Question.
You left off one of the most controversial applications is looking through people's walls of their homes. Apparently the police use this to see if people are home. Is it possible to do this?
No, we cannot see through objects. However, if you're cooking something illegal, I will see it from the exhaust of your.
Switch it off now, brother.
Another question?
In fact, we participated with some police people to
It's
measure.
not possible with this system.
No, but then we measured what was coming out of the
Vent?
fan, the vent of houses. Yes, to see some. It's an indirect way of knowing that something wrong is going inside the house, but we were not seeing through the walls.
Sorry for asking a similar question, but since you acquire 50 grams of different OPE as a function of time,
Yeah.
isn't the underlying assumption that the scene is not changing as a function of time? And having said that, I still don't understand how you construct the time variability for your movies. What's the assumption that you're making that makes this work?
Yeah, okay. So this is a really good question, but you're right. So when you measure a spectrum, you assume stationary. So you assume that the scene is like static and it doesn't change. If it does change, it introduces artifacts. So you have to work your mathematics in order to remove those artifacts to get the pure spectrum.
He said it was just a simple Fourier transform, but I was thinking at the time, it's not so simple.
I don't want to afraid anybody. But you're right. If the scene is not static, you might get some artifacts.
Like you have magic makes it go.
Yeah. Pardon me?
What's
You
the
have
secret?
magic.
No, well, yes and no. Sometimes there is nothing you can do, but sometimes yes, there are things you can do to remove those artifacts.
There's another question over here.
All the stuff that you showed has been passive, looking at scenes. Do you ever do stuff where you would have, say, a couple laser line sources next to the camera, backlighting the scene, and then doing spectroscopy with that?
No, we never put a laser in parallel, but however, we did put broadband sources just to illuminate the scene. So I didn't show it in my presentation, but we have some setup where when you want to measure nearby objects, and especially when you are indoor. When you are indoor, everything is at the same temperature, and an object just will reflect exactly the same temperature as it emits, so you don't have contrast. So if you want to produce contrast indoor, well, it's better to illuminate with like a broadband source. So, but we never tried with a laser, but just with broadband.
One more question?
One more.
For the optical path difference, you need to know exactly how much you move by. Do you have an optical encoder or a reference source for
It's a laser.
You use a laser.
Yeah, so inside the same cavity, in addition to the infrared signal, we inject a laser of a known frequency of
Diode
wavelength.
laser.
And in the hypercam, it's a helium neon laser. Yeah, it's very stable, very well-known wavelength. Yeah.
Thanks.
I have one question. What are the prospects for putting a system like this on a satellite?
Well, on satellites, there is some with fewer pixels, like the CRIS. So when we knew each other, because we were working on the CRIS for the endpost, so it's like a 3x3, so it's only 9 pixels.
And each pixel is like 10 to 15 kilometers.
Absolutely. So it's not real imaging. Teleps has been working with Harris recently for a small version of the Hypercam, which will be installed on CubeSat. Okay, but it will be a constellation of CubeSats that will fly one after the other to do 3D wind imaging. So and they have a bit more imaging capability than the CRIS, but not as the Hypercam. So I'm not aware of a mission, let's say a satellite-based mission, with that much amount of pixels. I'm not aware. Maybe there are people working on that. It's not me.
Okay. One last question.
Yeah. You just mentioned that gas can be detected. I just want to know whether you have the ground truth, whether the gas is how much is emitted, and do you have a quantitative number compared with the ground truth?
Yeah, so this is really, really interesting because when you do gas detection, so to detect it is like the easiest thing to do. To identify it, well, when you have a spectrometer, it's almost straightforward. But when you want to quantify, this is really the worst thing. So yes, we participated. So the only thing that people can easily measure when they release gas is the leak rate. So how much they release per minute. So, but what we measure with a system like that is how much there is. We don't measure the leak rate. To do the leak rate, we have to do more things. But and this is always the trickiest part, is to have real ground truth to compare with. So maybe I did too quickly. But when we were at Total, and I showed you these 3D things, here it is. So the ground truth, there was some ground truth, and as you can see, maybe, so here, oops, yeah, sorry. So here you have, so the release point was in the middle of those little yellow sticks, and on those sticks they put point detectors, so that they were measuring ppm level of gas. So they were trying to install those sticks depending on the wind direction to make sure that they capture the gas cloud. And I can tell you that we get better results with the African than with those point sensors, because you also saw, for example, when I show you the methane release, it's moving all over the place. So imagine that you have only one point sensor there. Maybe for a minute it will sense nothing because the wind is such that it goes elsewhere. So ground truthing for gas release is very, very hard.
Okay, well, I think we'll cut it off there. I believe there's cookies outside and coffee, and so Dr. Chamberlain will be around for another half hour or so, and if you have more questions, come on down. Thank you.
Thank you. I want to go to my screen.
Oh, okay.
Felix, this is
Hi.
John.
How you doing?
This is Felix.
So you're